Okay, good afternoon, everyone. I'm Amir Mushtaq Siddiqui, and today we'll be discussing about Quadtree. Okay, so before starting with Quadtree, I wanted to discuss about computer graphics algorithm. Now, computer graphics is actually widely used nowadays in a lot of fields like CGI, video games, image processing, VFX in movies and videos. And when we're dealing with computer graphics, we are not dealing with normal text data structures and integers and number data structures. Rather, we are dealing with objects like points, rectangles, circles, and other geometrical shapes. So now that we are starting with geometrical algorithms, we will be dealing with points and rectangles. Okay. Now, before moving on to the data structure itself, I believe the best way to understand the data structure is to first understand the problem that it solves, right? So let's first introduce you to the problem that we were facing, and we needed to solve this. So this is our system. Our system is a rectangle with lots of points and particles. This could be like a video game where in a rectangle or a square environment, there are many objects, different objects, and one of them is one of them is a player. Now, what we need to do is we need to detect collisions between different objects. So let me get the marker. So if we need to detect collision with of this object with all the other objects, we need to first get this object and then see if it is colliding with this and to see if it's colliding with this and this. And we need to see if it's colliding with all the other objects, right? One by one. And if we need to see if this object is colliding with any other object, we need to see if it's colliding with all the other objects. So we need for one object, we need to check it n times, and for all the n objects, we need to check it for n square times. That is, our time complexity becomes n square. So so the comparison for like if we have 100 particles, the comparison will be 100,000, 10,000, and it will exponentially increase. So we need to find a solution to this problem using geometrical objects. So the solution can be, or one of the solution can be, is that in collisions, we do not like we assume that this particular particle will not be colliding with a faraway particle like this anytime soon, right? We only need to detect collisions with the vicinity or all the particles that are in the vicinity of this particle. So if only we can get a region around this particle and say that get all the points in this region, and then we can do the collision detection between this particle and all the particles within this region. So our computation is much more faster, right? So what we need to do is that we need to subdivide our region into smaller regions, and whenever we want to detect the collision of one particle with the other particles, we just look at the particular region and then see if it's colliding with other particles. All right. And these particles are just simple points and spaces. And since we're dealing with 2D coordinate system, they are just a couple of values, x and y. So the solution is Quadtree. Now, what Quadtree does is that it divides our region, the region that we took, into four children's. That's quad, right? So quad means four children. So our region, this particular region, is subdivided into four regions, and this four region is again subdivided into four other regions. So now, if we want to query, if you want to see if this particle is being collided with the other particles, we can just simply do a range query over a subregion and say that we want all of the particles within that region, and we don't have to deal with all the other particles like these particles and these particles. We can just say that give me particles in this particular region, and then detect the collision of this particle with all the other particles. So this transforms now the number of subdivisions since the number of subdivisions is recursive. The parent contains four children and the child contains its four children. So since the subdivisions is recursive, we move from n square time complexity to n log n time complexity, like we see in any other tree and any other range queries, right? So we are skipping a lot of unnecessary collision detection systems, and we are reducing our time complexity from n squared to n log n. Now, why this is a tree? This geometrical shape. Why this is a tree? Is called a tree because of its recursive nature and its expanding nature. The parent object contains the information of its four child object, and its child object contains information of its four child object, and each child object is a quadtree in itself. If I separate this region in itself, this is a quadtree in itself. So this recursive nature makes it a quadtree. For example, the root node over here. Let me get a different color. So the root node over here is subdivided into four regions like these, and and one of the nodes is again subdivided into four regions, and one of the other nodes is subdivided into four regions, and this is a tree structure. Now, since we are familiar with trees, we can actually program it very easily, right? So, so one of the easiest way that I usually tackle this kind of problem is I first research about the topic like Quadtree. So let's go to the Wikipedia of Quadtree, because I believe that Wikipedia is a very good resource when you're dealing with computer science data structures, rather than Geeks for Geeks, because most of the, yeah, Geeks for Geeks is quite popular if we go there. But it only deals with the implementation of the core tree. You directly get the program. You do not get the entire aspect or the bigger scope of the core tree. So I usually refer to the Wikipedia for different data structures. If you have any other uh, preferences, that's good for you. Okay, so here we can see that the core tree was designed in 1974, and there are three points in a core tree that we saw, that which we using which we'll solve the problem, is that we decompose our space into adaptable cells, right? And each cell will contain points in itself, and when they will reach the maximum capacity, they will split. So let me go back over here. So let's say that the maximum capacity I want in a cell is say let's say is 4 points, right? So when I have 4 points in our space like this, what I'll do is I'll split the chord tree now. Now, yeah, so I'll split the chord tree. And now when the next point comes, I'll see in which region it lies. Like if it lies in this region, I'll store it in this region. And if the next 4 points come in this region, and now when the fifth point comes in this region, I'll split this region into four parts, and then I'll store it recursively like this, right? Now, the number of points or the density of points that one region stores will depend on will result in how fast our algorithm runs, right? If we have a high tolerance of points in one region, then that means that for each region there will be a lot of points for which we need to do collision detection, right? And if we have low number of points in one particular region, the problem that we'll see is that for each frame of data, we cannot undo a chord tree, right? If we do have a chord tree, we cannot delete a node and delete a particular structure. So the best way to refresh a chord tree when our new state arises, for example, if in a video game or in a video, if this particle moves to a different region, if it moves, let me get a different pen. If this particle moves in a different region in the next frame, we cannot just adjust this chord tree. We need to remake this chord tree. Right. Now, this is computationally expensive, but what it's providing, this range search in n log n, is far more superior than the cost of building the Quadtree in each frame. We can afford to build the Quadtree in each frame rather than do the collision detection in n square for each particle. Right. So if we have very less number of particles per region, the problem that we'll see is that we need to make more and more subdivisions for each particle, because usually in a normal image we'll see around 100,000 to a million pixels or a million particles or a million points, right? So if we have low tolerance in one particular region, we'll need more and more subdivisions, which will be computationally expensive for each frame of data when we need to rebuild the quadtree. So we need to find the right balance according to the computational needs that we have. All right. So these are the 3 points. We decompose the space into adaptable cells. When each cell reaches its maximum capacity, the bucket splits. And the tree directory, like I showed you in the previous slide, the tree directory stores the information of its children. Right. So these are the 3 basic points of Quadtree. Now that we know the 3 basic points of Quadtree, let's actually code it. Right. Now, this whole code, the Quadtree code that I made is available on the GitHub. I'll actually share the link of the GitHub with you all. Uh, yeah, because this will be because so that you can all follow along. I'll add this in the chat. You can clone this repository, and you can do a code along, or you can actually just follow the code. But I highly recommend you to actually clone the repository and see how the code is working, because it will give you a better understanding. Now, let's just include a standard repository and standard libraries and all that, and I'll be using tool as well. Okay. Now, when we're dealing with chord trees, like I told in geometrical algorithms, we need points and rectangles, right? So we need a data structure that can store the points. I believe that this font is too small. Let me get this bigger, more space. So we need a data structure that can store points, right? And the point is simply 2 values, float x and float y, and we can rename it to point. So now in C, now C since is not an object-oriented programming language, what I usually do in C is that to make it object-oriented, I make functions in with name like this. So if I need to make a function that is related to this particular data structure, I'll name it point, and then what this function does. So if I need to instantiate it, point new. So this is like a constructor to an object. The constructor takes 2 values, and it will return the point itself. So I'll do is I'll allocate memory to it. So this is what constructor do. And let's initialize the values. And let's return the point. Let's return the reference to the point. Okay, so this is the constructor. Now we can print this point. I actually already made a printing program for this. Let me just copy it over. So it simply just takes a point and print it nicely in format. Now, apart from point, what we need is rectangles, right? As we see, we need rectangles or regions that bound it. All right. Now, the term used for these rectangles in most of the textbook is axis aligned bounding box, AABB. All right. That's because the rectangle is axis aligned and it bounds the region. So the term that is used for this data structure is AABB, or axis aligned bounding blocks. Axis aligned, right? And what this will store is now there are different ways in which you can store the information of rectangle. So what I'll do, what I believe is the easiest way is to store the center point, this point, and store this point because we already have a point, and store the half dimension of it. I'll call it HT. So if we need to find this point, it's simply center point x coordinate minus half dimension and y coordinate plus half dimension. Right. So the data that it will contain is a point and a half dimension. That will be a float value. Call it half dimension. And let's rename it to AABB. Okay. Yeah. Now the functions that this bounding box needs to have. First, let's create a constructor for it. So it's again AABB reference. It will return a reference, and since it is an AABB AAB of object, I'll name it AABB, and we need a center value. This point center, and we need a half dimension HD. Right. Let's allocate a memory to it. I'll call it AB is equals to ABB enter and malloc. And let's initiate the values. AB center is center, and AB after half dimension. And let's return it. The operations that we need for an axis aligned bounding box is that we need to check if a point is inside the AABB or is inside the rectangle. Now, the way to check if a point is inside a rectangle is simply to see if the left edge of the rectangle, the x value of the left edge of the rectangle, is less than the x value of this point, and the right edge is more than the x value of the right edge is more than the x value of this point. Similarly for the y values. All right. So let me just copy over this function. This check is too long, and I'll go over what this function does. So this actually takes the boundary. If this function just sees if it contains a point. So this takes a boundary and a point. So we'll check if the point contains in a boundary. So we'll see that the x value is less than the center minus half dimension, that is the left edge. And if the right or if the x value is greater than if the x value is less than the x minus if the left value is less than the half dimension, I mean the left edge, then it is not inside AAB, so we'll return false. And if the if the x value is greater than the center, the right edge, that is center x plus half dimension, then it is not inside the AABB or the rectangle. Similarly for the y check, and will return false. If I'm going too fast, please do tell me, or if you have any doubt, please do tell me. I'll stop and explain along the way. Now, this is one check to see if a point is inside a rectangle or not. The second check that we need to see is that if two rectangles intersect or not. So because of the range queries, right? So in this, for example, if we need to do a range query of these 2 points of this region, we need to see which all rectangles actually intersect with this our range query rectangle, right? So we need a function that actually checks the intersection of 2 rectangles. So I actually, because there are too many checks, I actually made this function beforehand, and let me show you what it does. So it returns a Boolean value, that is if a rectangle intersects or not. It takes 2 rectangles, that is itself, and the other rectangle. So what it does is that what we need to do is we need to check if, let me go over this. So we need to check if this rectangle If these two rectangles are intersecting, there are only four ways in which two rectangles can intersect. This, 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 and this, right? So if the left edge of the other rectangle is less than the right edge of our rectangle, then it intersects. If the left edge of our rectangle is less than the right edge of the other rectangle, then it intersects. And similar for similar for both y's as well. So that's what I did. So if the left edge of our rectangle, if the left edge is calculated like this, because it's a half dimension rectangle, so the center x plus half dimension, sorry, the right edge. So the center x plus half dimension will give me this point, right? This point is the center. This is center plus half. Sorry, this is the right edge. So if the right edge is greater than the center x of the other minus half dimension, that is the left side. So center minus half dimension is the left side. Then it actually contains, and similarly for the other two sides, that if the left edge, similarly for the other four cases, the similar checks if the edges are intersecting or not. So if it does, then return true, and if it doesn't, then return false. All right. So now our geometrical helper functions like point and rectangle, that is called AABB, access line bounding box, is now ready. Now we do have both functions that we need to test if the point contains in it or not, and we have an intersection check as well. Let's move forward to the quadtree itself. Now let's define a quadtree. Type def a quadtree. We'll rename it to quadtree. Okay. So what all do we need to store in a quadtree? Right. The first thing that we need to store in a quadtree. Now let's go over here and see what a quadtree actually is. Right. Go here. So this is a quadtree. Now the quadtree is a rectangle itself, right? It is a rectangle which is an access line bounding box, or the AABB actually defines the region of the quadtree. So let's store a reference of it, which we'll call boundary. So AABB star boundary, right? So we do have a boundary. And the other thing that we need to store in a quadtree is the points, all right? The number of points in one region. So we need an array to store the points. So let's make an array to store the points. And the maximum capacity that one region will contain, we'll define it at the top. We'll say define Qt quadtree node capacity. For example, I'll take a low number like 4, right? And yeah, if in our example, I'll take a low number 4, but in real cases, the number will be in thousands, because checking collisions for 1,000 object, that is 1,000 times 1,000 n square, is not very computationally expensive, and we need the quadtree to be generated fast. All right, so I'll take 4 for example. All right, so the other thing that we need to store in the quadtree. The quadtree has 4 children. All right, 1, 2, 3, and 4. This one, and this one. So we need references to these 4 children, and these 4 children are quadtree in themselves. So we need a reference to the 4 children. Now the 4 children is the northwest child, the northeast child, southeast child, and the southwest child. This is our quadtree. Hope this much is clear. And now we need a constructor to actually construct this quadtree. I'm using object-oriented terms in here just because I'm following the object-oriented paradigm. But I hope this doesn't confuse us here. All right. So we need a constructor that will follow the same naming scheme, Quadtree Neo. Now to define a quadtree, we need a boundary of it. So we'll take a boundary as a parameter. And now let's allocate the memory to the quadtree. Allocate memory to the quadtree, and we'll say it's QD is equals to quadtree star malloc size of quadtree. Now let's store the boundary of it. And now we need to let's initialize all the childs as null. So qt of northwest equals to null for all shells, northeast, southwest, southeast. Right. And now we need to initialize the points itself, because points is a constructor, because points is a pointer, so we need to allocate memory to it. So qt of point will be, we need to allocate memory to it because it's an array. Point malloc size of point enter into qt capacity. And we need to initialize all of this. And we need to now initialize and now return it. Right. Now we do have a quadtree, we have rectangle, we have a point, and yeah, so now we have all the tools that we need. Now we need to start the operation. Now the first operation that we want to do is to create the quadtree. Now to create a quadtree, we need to store the points in the quadtree. So let's create a function that stores the points in the quadtree. It will return a bool to tell if a point has been stored or not. Insert. Let's actually, since we are less on time, actually I'll just show you. I'll give you the basically. Okay, so let's see how the insert function actually works. So before inserting, we just need to check if the point actually is within the boundary or not. Remember, we actually created a function that checks if a point is within a boundary or not. So ABB contains, we check if the boundary of the root node or the quadtree is within the point or not. If it isn't, then return false. And if it is, the point is within the boundary, what we'll do is we'll insert the point within the Qt node capacity, within the points array of the quadtree. And if it exceeds the Qt node capacity, then what we'll do is we'll store the point in the child of the quadtree. So if we'll first check if the child actually exists or not. If it doesn't exist, then we'll subdivide the quadtree. We'll see how subdivide works later. After subdividing the quadtree, we'll try to insert the point in any one of the child nodes, starting from northwest, then northeast, southwest, and southeast. And if it gets inserted, then we'll return true. And since we are actually checking if the point is within the boundary or not, it will recursively check if the point is within the boundary of northwest region, northeast region, southwest region, southeast region, and will appropriately insert in the particular region that they have. Now let's talk about the subdivide of the quadtree. Now we need to subdivide the quadtree whenever we're inserting the node, whenever the point capacity reaches its max. So let's copy over the subdivide function. Right. That's the subdivide function. What it does is that when we're subdividing, let's go over there again. Okay, so let's over here. So when we're subdividing a quadtree, what we'll need to do is that we need to find the four centers and the half dimensions of it. So the first center is over here, and the half dimension will be HD by 2, HD by 2, and the center of it will be C minus HD by 2 and C plus HD by 2. All right. So the northwest region will be center minus half dimension by 2, and Y region half dimension plus 2. We'll make the quadtree using that region, using the constructor that we created. Similarly, for the northeast region, we'll do the same. We'll find the center and we'll make a bounding box of half dimension, and we'll create the quadtree. Similarly, for the southeast region, and we'll assign it all in the root of northwest, root of northeast, or root of southwest and southeast, and we'll return the root. That is, the tree is subdivided, right? So once the tree is subdivided, so this is the insert operation. This is how we'll be inserting the quadtree, and this is how the quadtree is made. Now, what I did to demonstrate, because this is all code and it's not visually, if we can get the visuals of it, it'll be very intuitive, right? So I went ahead and made the similar thing in JavaScript, and I used some SVG libraries and graphic libraries to actually show how the insertion works. So I did the same thing. We have a point class, we have AABB class, which has intersects function. We have a quadtree class, which has all the function, the subdivide function, insert function. And in the insert function, I just use the SVG to actually draw it. All right. Let me show you this. Okay, so this is the application that that I made using the Quadtree. This is all available in the GitHub. You can actually clone the repository and play around with it yourself. So let's first make the initial bounding box to see how it actually works. So I'll make the center as the center itself, and I'll make the bounding half dimension as 200. Let's create it. I hope this is visible. Now let's start, and this is the root node of the tree itself. And now let's start adding points. Now I can actually manually type the points in here, 20, 40, and add it, or I can just add random points. Now I changed the node capacity for our example to 2 so that we can see the subdivisions more clearly. Uh, yeah, see, I changed the node capacity to so that we can see the subdivisions more clearly. So now I inserted 2 points, right? Let me zoom in here. So I inserted 2 points. When I insert third point, it will subdivide the quadtree into 4 different regions, these 4 regions, and will store the quadtree in the appropriate region. Now, again, as we are adding more points, and once this region reaches its capacity, and when the third point is added, it is again subdivided into 4 regions. Let's add 10 random points to see how it works. See, as the points are increased, the subdivisions are increased and points are stored in the appropriate subdivisions. If I add more points, we'll see that there are more subdivisions and the tree structure is increased appropriately. So this is all about the insertion and the creation of a quadtree. Let's see how we query into a quadtree, and hopefully that will be the end of the lecture. So let's do the insertion, the querying of the quadtree. Now to query, like I told in my slide before, to query a quadtree, we need a bounding region. We'll give the quadtree a bounding region and we'll say retrieve all the points within this bounding region, and we'll check the collision detection system with or anything else, or the other application that we want to do on these points. But we need a bounding region to query it, right? To query the range. So we'll pass in our quadtree and we'll pass in a bounding region, AAPB range. All right. Now let's see how we actually query into a quadtree. Now I created an array to store all the results. I gave it a max array size of 1024 points, so that it doesn't exceed, because 1024 is enough for a demonstration. And I'll initiate it all the points as null. Now what I'll do is I'll first check if the range region actually intersects with our root boundary, or actually intersects with our the bounding region of a root node, because if it doesn't, then because if it doesn't intersects, then the range query will not work and will return an empty array. So this is to skip a computation. Now, now what we'll do is we'll iterate over all the points within this region, and see if the region, the boundary of this, actually contains, or the range of it actually contains any of the points. Now, remember, we actually created this contains function. So we'll pass in the range and we'll see all the points in this region, the root region, and see if it actually contains in it or not. And we'll store all the resulting points in our result array. Now we'll see if this particular region has subchilds or not. Now, since it's always divided into 4 children, we can check any one of the children and see if it's null or not. And if it is not, if it is null, then return the result itself. That is, this is the leaf node. And if it is not null, then what we'll do is that we'll query into each region itself, recursive. Right. So we'll query range into the northwest region, we'll query range into the northeast region, we'll query range into southwest and southeast region. We'll retrieve the result of all the regions in the appropriate arrays, and we'll store the result in our result array, right? And we'll return the result array. This way, this is how we do the query region, the querying function. Now let's do a demonstration of it, how it actually works. Let's make it. Let me increase the size of it. Let's compile it. Let's run it. Now, I actually made a printing function for the bounding box itself on the terminal so that it's easier for us to see. Now, the center, let's make it 0 and 0, and let's do the half dimension as 10. So this is our query tree boundary. This is minus 10, 10, 10, 10, 10 minus 10 in this. And we'll start inserting the point within this region. So let's say we'll insert 5 points, the first point being 2, 2. If we go outside the boundary, like 12, 5, it will say the point is outside the boundary and not inserted, because remember, we actually put it a check. Uh, we actually did a check when we were inserting to see if the query is actually inserted or not. If it is not inserted, then that means it's outside the region. Let's do a third point, that is 4, 4. Let's do another point, 8, 8, and then 6, I will, okay, so all the points are inserted. Now we need a bounding region to actually query into our quadtree. Let's make a bounding region again centered at 0, 0, and we'll give it a half dimension of 5, 5. Right. So this is our bounding region, minus 5, 5, 5, 5, minus 5, minus 5, 5, 5. And all the points within this bounding region using our algorithm are returned 5, 2, 2, 4, 4, 5, 4. So this is all about Quadtree. Now, there are several applications of Quadtree. For example, mesh generation. In mesh generation, the meshes are actually the way of recognizing an image to 2D objects or 2D geometrical objects, right? So we can pass in the pixels of the shape that we want the mesh to be generated, and we can subdivide accordingly to the mesh itself, and we can then triangulate these squares to generate our mesh. Okay, so this is all about Quadtree. I hope it was informative. Thank you for listening.